Welcome to example 7. We have a box that is being pulled along this level surface, and it's being pulled by this string that makes an angle of 30 degrees to the horizontal. So we're asked to find the horizontal and vertical components of that tension, the normal force acting on the box, and the coefficient of friction between the box and the surface. So the first thing we'll do before we start proceeding with the problem is we're going to draw a free body diagram for the box. Let me redraw the box over here. So what forces do you think are acting on this box? Take a moment, maybe stop the video and draw your own free body diagram, and then press play and see if you get the same thing as what I'll have. Okay, so we know that there's a string pulling on it, so we should have a tension off here at an angle of 30 degrees. We'll label that as F sub t for tension. We also have a force of gravity pulling it straight down. We'll label that as F sub g. Then we have a normal force acting upwards, around about maybe here, I guess. And we'll label that as F sub n. Now, since the box is moving to the right, and this surface is not frictionless, there is a frictional force acting in the opposite direction that it's moving. That's because it's going at constant velocity. And friction is opposing the direction of it that it's moving. So in part A, we're asked to find the horizontal and vertical components of that force of tension. So we're going to find F sub tx, and we need to find F sub ty. I'm going to show the tension x component and the y component. I normally would show it in the diagram here, but I don't want to clutter up my free body diagram. So I'm going to redraw that tension over here and make a triangle with the x and y components. So there is our tension right here. And then we're going to show the x component now. We'll label that as F sub tx. And there's the y component, but I want to make a triangle out of that, so I'm going to move that over here. So there's F sub ty, and this is at a right angle of these two components. And this angle over here is 30 degrees. All right, now we know that this rope is pulling with a force of 260 newtons. So if we're trying to find the x component, what trig ratio would you use? This is the adjacent side, and this is the hypotenuse. Hopefully you see that would be cosine of the angle, cosine 30 degrees, equals the adjacent over the hypotenuse, which is 260 newtons. So the x component of that tension will be 260 newtons multiplied by cosine of 30 degrees. That'll give you an answer of approximately 225 newtons. And we'll put a box around that answer. Okay, let's go on to the y component. To find the y component, we're going to be using the opposite at the hypotenuse, so that would be sine of 30 degrees equals FTY divided by 260 newtons. And the y component will be equal to 260 times the sine of 30 degrees, which gives you an answer of 130 newtons. Okay, now let's move on to what is the normal force. So we'll move on to part B here. Now, when you look at this body here, it is moving along here at a constant velocity, which means that the acceleration is 0. So the sum of the forces in the x and in the y are 0. In this case, we're going to be examining in part B the forces along the y-axis because we would like to find the normal force, which is along the y-axis. Good idea at this point is probably to state what we're defining as our x and y axes. So I'm just going to add these dashed lines here and say this is the x and this is the y. So that's a positive x along here and positive y going upwards. So let's take a look at the forces on the y-axis. They should balance out to give you 0. So this means add all the forces along the y-axis. Now remember, now the tension, we're going to replace it now with its x component and a y component. So if we sum the forces along the y-axis, we have a normal force up, the y component of the tension up, and then we have weight going down. And all of these forces give you 0. They add up to 0. You could also just state it as the normal force plus the tension in the y direction is equal to the weight. These two forces will combine to add up to the weight. So we're looking for the normal force. So the normal force will be equal to the weight minus the y component of the tension. And the box, by the way, I should have wrote down the given in here. We know the tension is 260 newtons. The weight of the box is 450 newtons. And so we know the weight. So we know the weight is 450 newtons, and we know the tension over here was to determine the y component of that tension was 130 newtons. So it turns out that the normal force is equal to 320 newtons. It is less than the actual weight. Why? Because that part of that tension, part of it is pulling upwards and making the ground below push with less force because the rope's helping it a little bit. Okay, on to part C, the coefficient of friction. In this case, it will be called kinetic friction because we're moving. So moving friction is called kinetic friction. So on part C, to find the coefficient of friction, if you recall, is equal to the force of friction divided by the normal force. So we know the normal force. We now need to find that force of friction. So where is that going to come from? We have to apply Newton's first law along the x-axis. So the sum of the forces along the x-axis, it's not accelerating again. Why? Because it's moving at a constant speed and in a straight line. It's constant velocity. So the sum of the forces is equal to 0. So what's balancing out horizontally now? It's the tension in the x direction that is counterbalanced by the friction. So we have the tension in the x direction minus the force of friction, and these both add up to give you 0. So the force of friction is equal to the x component of that tension that we determined earlier, which is equal to 225 newtons approximately. So if we want to find the coefficient of friction, mu, we take the force of friction and divide it by the normal force. So it's 225 newtons divided by 320 newtons. And that gives us an answer of 0.703. Notice there's no units because the newtons and the newtons at top and bottom will cancel. And that's it for this example number 7.